Measures of position. The z-score. It is believed that the mean top speed of a rabbit is approximately 35 miles per hour, and the standard deviation is believed to be approximately 4.5 miles per hour. The snowshoe rabbit is believed to have a top speed of approximately 27 miles per hour. It is also believed that the pace of a tortoise is approximately 0.09 meters per second, and standard deviation is believed to be approximately 0.02 meters per second. According to the Guinness Book of World Records, Birdie, the fastest tortoise ever recorded, is capable of a speed of 0.28 meters per second. While a slow rabbit is certainly faster than a fast tortoise, we are usually more concerned with the position a data point occupies within the distribution of its own data set. One measure that is used for this purpose is the z-score. The z-score represents the number of standard deviations that a data falls above or below the mean. In calculating the z-score, we will subtract the mean from the data point, then divide by the standard deviation. So assuming rabbits have a mean top speed of 35 miles per hour and a standard deviation of 4.5, a speed of 27 miles per hour would fall 1.78 standard deviations below the mean. Negative z-scores indicate that a data value falls below the mean. Assuming tortoises have a mean top speed of 0.09 meters per second and a standard deviation of 0.02, Bernie's speed of 0.28 meters per second would fall 9.5 standard deviations above the mean. And positive z-scores indicate that we have a data point that falls above the mean. Percentiles. Percentiles divide a dataset into 100 equal groups. The symbol p sub 10 refers to the 10th percentile, and it represents the point at which 10% of the data values in the sorted dataset lie below the value and 90% lie above. For instance, if your score on a standardized test places you in the 57th percentile, then the symbol p sub 57 would be used to describe your relative position in the population. The interpretation of the symbol would be to say that 57% of the students taking the test scored below your score and 43% scored above your score. The percentile corresponding to a given value x is computed by using the following formula. The number of data values below x plus 0.5 divided by the total number of values, then multiplied by 100. These data values represent the median household income for all counties in the United States, including Puerto Rico, according to the 2012 to 2016 American Community Survey. Suppose we wanted to find the percentile ranking for the median household income for Kearney County in the state of Kansas. According to the survey, Kearney County is number 1,985 in the sorted list. So the number of data values below would be 1,984. Carrying out this calculation, we would find a value of 62 when we round it up to the nearest whole number. Percentiles should be reported as whole numbers, because if we were to include decimal places, it would imply more than 100 positions in the dataset. Here, we would use the notation p sub 62, which would be interpreted by saying 62% of the counties in the United States have a smaller household income and 38% have a higher household income. Quartiles and the 5-number summary. The July 1st to June 30th annual rainfall in Los Angeles for the years 1997 to 1998 through 2016 to 2017 is shown below. The data values represent inches of rainfall. Let's begin by finding the minimum data value, the median, and the maximum data value for this data set of 20 data values. We can facilitate this process by first placing the data values in order. Now we can easily see that the minimum value is 3.21 and the maximum value is 37.25. The median for an even number set of data is the average of the middle two values once the data set is ordered. We can find the median by adding 9.65 and 11.57, then dividing by 2. This gives us a median value of 10.61. Let's continue our analysis of this dataset by finding the quartiles. The quartiles divide the dataset into 4 equal parts. The first quartile, which is abbreviated Q sub 1, separates the bottom 25% of the dataset from the top 75%. The second quartile separates the bottom 50% and the top 50%. This is also known as the median for the dataset. The third quartile separates the bottom 75% from the top 25%. The first quartile is determined by finding the median of the first set of values that fall below the median for the data set. There are 10 values in the bottom 50% of the data set, so the first quartile we found by adding 8.52 and 8.69, then dividing by 2. So the first quartile will be 8.605. The third quartile is found by determining the median for the top 50% of the data set. We will find this value by adding 16.49 and 17.94, then dividing by 2. The third quartile is then 17.215. We now have a list of 5 measures that are resistant to extreme data values. This list of 5 values, the minimum, the first quartile, the median, the third quartile, and the maximum, are called the 5-number summary. Now let's follow along with your student notes. Measures of position are used to locate the relative position of a data value in a data set. A value at the 88th percentile has 88% of the data values below it and 12% above it. The median is a measure of position corresponding to the 50th percentile. Standard scores can be used to compare the position of data values on 2 different distributions by providing a measure of how many standard deviations a particular data value is from the mean. Formulas for standard scores are calculated as follows. We will utilize this formula here for samples and this formula here for populations, where x is a data value, x bar is sample mean, mu is a population mean, s is the sample standard deviation, and sigma is a population standard deviation. Let's do an example comparing 2 distributions. Did a student perform better on a calculus test with a score of 65, having a mean of 50 in the class and a standard deviation of 10, or on a history test with a score of 30, having a mean of 25 and a standard deviation of 5? Notice here that 65 and 30 are both above their respective means. 65 is 15 points above the mean of the calculus test, which is 1.5 standard deviations above the mean. 30 is 5 points above the mean of the history test, which is 1 standard deviation above the mean. So clearly, the student has a higher relative position on the calculus test. Keep in mind, it's not because the score is 65 versus 30. It's all because of how far away it is from the mean, and in particular, how far above it is from the mean. Another way to solve this, we can actually use the z-score or standard score formula to determine how many standard deviations above or below the mean a data value is. For the calculus test, z equals to 65 minus 50 divided by 10, which once again leaves us with 1.5, meaning 1.5 standard deviations above the mean. For the history test, 30 minus 25 over 5 gives us 1, which again means 1 standard deviation above the mean. So once again, the z-score for the calculus test is larger. So the relative position in the calculus class is higher than the relative position in the history class. Percentiles. Percentiles divide a dataset into 100 equal groups. The pth percentile is a value for which about p% of the data values are less than, and for which about 100 minus p% of the data values are larger than. Here's the formula for percentile. Notice that we take the number of values below the specific data value, add 0.5, and then divide it by the total number of values in the dataset n. And let's not forget to multiply by 100. P equals percentile. C will be the number of data values below a specific data value. N will be the total number of data values in the dataset. So the formula is a bit more clear if written like this. P equals C plus 0.5 divided by N times, again, 100. And the formula to find the data value that corresponds to a given percentile is as follows. C equals to N times P divided by 100. It is important to note that if C is not a whole number, we must round up to the next whole number. Then, starting at the lowest value, count over to the number that corresponds to the rounded up value, which I will show in an example very soon. However, if C is a whole number, we will use the value halfway between the cth and the c plus first values when counting up from the lowest value. Again, I will show shortly in an example. Let's find some percentiles. A teacher gives a 20-point test to 10 students. The scores are arranged in order from lowest to highest. Let's first find the percentile for a score of 12. Then we're going to find the value corresponding to the 60th percentile, and then we'll find the value that corresponds to the 65th percentile. Here once again is the ordered list. Here C equals to 7, since 12, as we can see, is in the 7th position in the ordered list. Since there are 10 students, n equals 10. Plugging these values into the formula, we get 7.5 divided by 10 times 100 gives us 75%. Thus, 12 is in the 75th percentile. In other words, the student who scored 12 is in the 75th percentile of the class, meaning that 75% of the other students fall below this score. For solution B, let's find out which data value falls in the 60th percentile. Since there are 10 students and P being the 60th percentile, we can go ahead and use the other formula. And as we can see, C here equals to 6. In other words, the 6th position. Since 6 is a whole number, the percentile is the value that's halfway between the 6th and 7th values when counting up from the lowest value. The 6th value is 10, and the 7th value is 12. Thus, the 60th percentile is 11. To verify, since again 6 is a whole number, the percentile is going to be the value that's halfway between the 6th and 7th values in this case, or smack dab in the middle of the data set. Since our data set here is even, we once again must add up and divide by 2 the middle two terms. The solution for C, where the percentile now is 65, plugging in the values, we end up with 6.5. Now this time, since 6.5 is not a whole number, we must round up to the next whole number, which is 7. Now, count over to the number that corresponds to the rounded up value. Since the 7th position, or 7th value, is 12, then the 65th percentile is 12. Now this may trouble you, only because in part A, the 75th percentile was also 12. Well, when you have such a small set of data, with only 10 students, sometimes data values can take up multiple percentiles. When you have a very large data set with many, many values, sometimes each percentile can take on many data values. Again, to verify, 6.5 means we round up to the 7th place. 1, 2, 3, 4, 5, 6, 7, which is why, once again, 12 is the 65th percentile. Quartiles. Quartiles divide the distribution into 4 equal groups, denoted by Q sub 1, Q sub 2, and Q sub 3, representing the 25th, 50th, or median, and 75th percentiles. To find data values that correspond to Q sub 1, Q sub 2, and Q sub 3, first, arrange the data set in order from lowest to highest. Then, find the median of the data values. This is also known as Q sub 2. Next, we find the median of the data values that fall below the median. This is called Q1. Next, find the median of the data values that fall above the median. This is called Q sub 3. Keep in mind, we can use technology to find these items. Let's do an example. Find the data values corresponding to Q sub 1, Q sub 2, and Q sub 3. First, let's go ahead and put these values in order. The median of these values, or Q sub 2, is 18. Now, let's list the values that are less than the median. The values that are less than the median of 18 are 12, 13, 15, and 16. Now, we're going to find the median of this list. And the median of this list, or Q sub 1, known as the first quartile, giving us 14. Let us now do the same, but for the values that are greater than the median. So here, we're going to go ahead and add the middle two terms, divide by 2, giving us Q sub 3 of 23.5. Let's try that again. Now here, I invite you to pause the video and try to do this yourself and come back and see if you have the same solution as me. In fact, feel free to use your TI-84 to try to solve this problem. Once again, let's put the values in order. First, we find the median of this particular problem. Here, since I have an even number of values, I must add the middle two and divide by 2. Now let's list the values that are less than the median. Here we have an odd number of data values, so clearly the median of this list is 17. We shall do the same for items that are greater than the median. Again, an odd list of numbers, which means 31 is our Q sub 3. Another important fact that we must know about is the interquartile range, which is the difference between the third and first quartiles. Outliers. An outlier is an extremely high or extremely low data value when compared to the rest of the data values. The mean and standard deviation can be strongly affected by X. Thus, they are non-resistant statistics. The median and interquartile range are less affected by outliers and are called resistant statistics. To identify outliers, first, arrange data in order from lowest to highest. Second, find the interquartile range. Third, multiply the interquartile range by 1.5. Fourth, find the upper outlier boundary, which is Q sub 3 plus 1.5 times the interquartile range. Then find the lower outlier boundary, which is Q sub 1 minus 1.5 times the interquartile range. Then check the dataset for any data value that is not between the boundaries. Let's check the dataset for outliers. Notice that it's already in order from lowest to highest. And we can go ahead and see that our first quartile is 17 and the third quartile is 31. Therefore, our interquartile range is 14. To find the lower outlier boundary, we go ahead and subtract from the first quartile 1.5 times the interquartile range. As you can see, it's 17 minus 1.5 times 14, which ends up being -4. The upper outlier boundary will be the same, but with addition. In this case, we end up with 52. Now, since the outliers of the data values must be smaller than -4 and also greater than 52, then thus, in this case, there's only one such outlier, which is 54.